allow me to recording of the session. Um, all right, so today we are going to discuss about the air pollution control techniques, air quality regulation in Pakistan, how to calculate air quality index, air pollution health impacts, economic benefits of improving air quality. These are the 5 topics that we're going to discuss today in the next 4 hours. For the first session, to start with air quality control techniques, we have with us Dr. Zeeshan Ali Khan. Dr. Zeeshan is working as an associate professor at NUST and heads the environmental engineering department. Before joining NUST, he has also served in Fuji Fertilizer Company, Pakistan, in operation and department. He has the PhD and MS degree in environmental engineering and management with a bachelor degree in chemical engineering. Dr. Zeeshan has research interest in the areas of air pollution management, energy and emissions, waste of energy conversion, and renewable energy. So, Dr. Zeeshan, welcome to the session. Thank you for having us. So, I'll stop this screen, and Dr. Zeeshan, you can share your screen, please.
Thank you, Ali. Good morning and Assalamu alaikum, everybody. I hope I'm audible and visible, and my slides are also visible.
Yes, sir, you're audible, visible, and slide are also visible, and you can do it on the full screen. Yeah.
Okay, thank you, Ali, for confirming. So, in the next 1 hour, we are going to talk about air pollution control techniques. I hope everybody is charged, and I hope everybody has had good breakfast, cup of coffee, so I won't have to work really hard to keep you awake and with me, right? So in this 1 hour session, we're going to talk about the reasons for the control of emissions, air pollution control. And we are going to talk about the options that we have for air pollution control, right? And mainly we are going to talk about two major options, one of which is cleaner production techniques, and the other one is end of pipe treatments. Before we move on, I would like to differentiate the two terms right here. Cleaner production technique means all those techniques that we use with one objective, and that is to reduce the production of emissions. Suppose you have to produce 1 ton of cement, right? And for 1 ton of cement, we produce, let's say, X tons of emissions, right? All those efforts which are done to reduce those emissions, we produce the same 1 ton of cement, but producing lesser amount of emissions, less than X ton. All these efforts would be categorized as cleaner production techniques, right? But no matter to what degree we reduce the emissions, still there would be some emissions, right, at the end of the process. So to cater those emissions, we have end of pipe treatment, right? And we are going to talk about both of these options in details in the coming slide. Of course, we are going to start with why industry goes for emission reduction. The major reason for industry to go for emission reduction is to meet the regulations, right? We need mass production. That's why we have industry, because we have got human population, and we have to produce goods on industrial scale for that. So we have to keep the industry running, right? But with production of the necessities and accessories, we produce a lot of emissions, right? And those emissions have got impact on the community, and to protect the community and the environment from the impact of those emissions, we have certain regulations industry needs to meet those regulations, and that is why it needs to control the air pollution, right? Another reason is to recover valuable products. In some cases, the emission streams have got some valuable product in them, right? So before venting those emission streams into the atmosphere, we need to recover those valuable products, and that's another reason to control air pollution. If an industry has to operate in a location, on a location, it has to have good relations with the people living in the vicinity, and those are possible if those good relations are possible if the industry takes care of its emissions, right? Similarly, sometimes the market also demands the control of air pollution, right? For example, to sell your product in certain markets, you need certifications like ISO 9000, ISO 14000, and other similar certifications. You must have heard those about those in their marketing campaigns. In the marketing campaigns of industry, they say that their products are certified by scientists, and all those some of those certifications require the arrangements and the mechanisms of air pollution control in place, right? And another reason to control the air pollutants for an industry is to maintain a healthy environment for the people working on the industry, right? So these are few reasons which make the industry go for pollution control. Now, if we look at the cleaner production techniques, we would talk briefly about cleaner production techniques, and then we move on to the end of pipe treatment. We have got certain options in our under the cleaner production techniques. For example, sometimes we reduce the air pollution production by changing raw material or fuel, right? I hope you all know, for example, the sugar can be produced by using sugarcane or the beetroot, right? And in either case, we have to pass the raw material through a sequence of unit operations or sequence of steps in order to convert those raw materials to sugar, final product, right? And I hope we all understand that for the two raw materials, the sequence would be different, right? You would pass the beetroot through a different sequence, you pass the sugarcane through a different sequence of steps in order to achieve the sugar. So if the sequence of steps is different, it means the energy consumption per ton of sugar produced would also be different, right? One sequence, one raw material would be consuming lesser energy than the other. Ultimately, you get energy from the fuel, right? You burn fuel, you get energy. So you would be burning less fuel in case of one raw material than the other. So sometimes changing raw material can lead to achieving less air pollutants per ton of product or per unit of product produced. Similarly, we always have the option to shift to cleaner fuels, right? 1 ton of coal, for example, packs less energy than 1 ton of gas, right? So you burn 1 ton of gas, you get more energy, you produce less emissions. So shifting to cleaner fuels is also an option to reduce emissions. Another option that we have under cleaner production techniques is instrumentation and control updates, right? Industry is extremely complex place, right? There are lots of machines, lots of equipments working in coordination with each other, and that is only possible because of a lot of instrumentation over there. A lot of sensors are involved, a lot of small microprocessors and process controllers and different types of computers are involved in instrumentation and controlling the process. And you can imagine that over last 30-40 years, this science of sensors and computers have progressed significantly, right? So imagine if a plant was erected, let's say 40 years ago, and there are like most of the plants are normally 3 to 4 decades older, right? So that is equipped with, those plants are equipped with instrumentation of that time. So sometimes improving the instrumentation and control leads to better control of the process, right? And that saves you a lot of energy. Ultimately, that reduces a lot of emissions or air pollutants per unit product. Similarly, we also achieve lesser pollutants by adapting modern technology. You must have observed in your homes that you replace the older bulbs and tube lights with energy savers, for example, because energy savers give you same amount of light, but that consume lesser electricity, right? That's what we call energy efficiency technically. So in industry, we use lots of motors, turbines, boilers, furnaces, and so on, a lot of equipments. And we are getting, day by day, we are getting more energy efficient machines and equipments. So if we incorporate more energy efficient equipments and technology into our industry or into our vehicles for that purpose, we get more output out of the machine consuming same amount of fuel, and that's how we achieve lesser emissions, giving us same amount of output, right? Sometimes we change process in the industry in order to reduce emissions. For example, you must have heard about catalysts, right? Now, catalysts make the reactions easier, which means you would be achieving same chemical reaction at lesser temperature or lesser pressure conditions, right? And in industry, we have hundreds of chemical reactions involved. We have got reactors in which the raw materials react with each other to form final product, right? So just take an example that we get a more kind of more sophisticated catalyst or more efficient catalyst, which can deliver us same chemical reaction at lower temperature and lower pressure. So lower temperature and lower pressure means you would be saving a lot of energy and but achieving the same objective, right? So you change that catalyst. So it means you're modifying your process, right, in order to decrease the fuel consumption and leading to lesser emissions. Right? Another option that we have in cleaner production is maintenance and inspection. A poorly maintained machine, even a poorly maintained car, for example, gives you less mileage for a liter of gasoline. Right? And the same goes true for all the machines and equipment involved in industry. So if we have got maintenance schedule in place and equipment machines are maintained, well maintained, it means they would give you more output for less inputs, right? Similarly, production coordination is also an important technique that we use for cleaner production. Industry is particularly the larger industry like petrochemicals and cement industry and oil refineries. They are big units, right? And they are divided into smaller units. For example, boilers are combined in one unit. Group of people operates all those boilers, and another group of people operates, for example, compressors. And industry is divided into different kind of subsectors, right? So there must be a good coordination among all those sectors, and that also helps us saving a lot of energy and ultimately we reduce emissions. Sometimes we modify equipment, whether that is due to process change or due to technology update or whatever reasons, and that saves us energy and that helps us in reducing air pollutants, right? So these are few options that we have under the category of cleaner production techniques to reduce air pollutants. Now, one thing we have to understand right here is that cleaner production techniques can reduce emissions, right? But in most of the cases, they can't eliminate the emissions. We would always have emissions as long as we are burning fuel, and sometimes the process also generates some emissions. So we would always be having some emissions, right? And for that, we have end of pipe treatment, right? The second category that we are going to talk about today. What we mean by end of pipe treatment is we have got a process, and this process can be anything. This process can be cement manufacturing. This process can be let's say, engine in the vehicle. So at the end of this process, of course, we would be getting certain product, right? And that product can be, let's say, oil or cement or sugar or fertilizer or anything. But with that product, we would get an emission stream, one or more emission streams, right? And one option that we have is that we vent that emission stream into the atmosphere without treating it. The other option is that before venting that emission stream, by the way, we would be referring to that emission stream as dirty gas, right? The gas, the emission stream which is coming right from the process before treatment, that is what we are going to call as dirty gas in this session, right? So we pass that dirty gas through certain equipment, right? And that equipment removes one particular pollutant out of that dirty gas. That dirty gas is supposed to be a mixture of gases, right? Some of those gases may be harmful, some of them are less harmful, some are more, some are not harmful, right? So normally this dirty gas is a mixture of gases. Some of those gases are declared as pollutants, and one control device removes one particular pollutant out of that dirty gas, makes it comparatively cleaner gas. Remember, we are not saying that the control device is eliminating the pollutant out of that dirty gas. Rather, it just makes it relatively less dirty gas, relatively cleaner gas, and then sometimes we have a series of control devices, right? We pass dirty gas through a series of control devices, and then we vent it after making it relatively cleaner gas, right? So end of pipe is a conceptually simple but maybe expensive. And the limitation of end of pipe treatment is that it converts waste into one form from another form, right? It converts one form of the pollutant into another form. It doesn't eliminate the pollutant in most of the cases. Rather, it converts the pollutant in less harmful way, and that's the objective of adopting um, end of pipe treatment. So we divide end of pipe treatment into two parts. One is stationary source, end of pipe treatment for stationary source, and the other is for mobile source. Now you can imagine that if we can use a particular device or particular technology for stationary source. Stationary source means a stack, for example, from industry, right? And over there you have got a lot of space. You don't have limitations on weight. You don't have kind of space limitations. So, but if you shift on a mobile source like vehicle, over there you've got lots of limitation. You have limitation of space. You have limitation of weight, and sometimes the nature and characteristics of the pollutant also determine also a factor that we have got. We divide the the control technology for um, air pollution into two categories. One is for stationary source and the other one is for mobile sources, right? And another thing that we have to understand is that we also, because the nature of the particulate matter from the gaseous pollutant is extremely different, so that is why we also divide the technology into two categories. One is for gaseous pollutant controls, and other one is for PM control. So we are going to divide our rest of our talk into four parts. Number one, air pollution control techniques for stationary sources, and within that stationary sources we are going to talk about PM control and then the gaseous pollutant control, and in the next part we will discuss control techniques for mobile sources. Again, in mobile sources we are going to divide that talk into two parts, for PM and for gaseous pollutant. So please keep this categorization in your mind for the next for the remaining part of this session, so that we can make it more meaningful, right? So as we discussed, first we will talk about the end of pipe treatment options for stationary sources, right? And among that stationary sources, we have got the uh, options to control gaseous pollutants and the technology options to control the particulate matter. Of course, we would start with the particulate matter, right? Stationary sources and particulate matter. That's the combination that we're going to discuss. One very basic technological option that we have to control particulate matter out of this stationary source is gravitational settling chamber, right? It's a very simple settling chamber. I mean, what we do is we have got inlet of dirty gas, and then that dirty gas gets a large cross-sectional area, right, to flow through. And this large cross-sectional area decreases the velocity. Just imagine that same amount of gas is passing through a small pipe, and then the same amount of gas is passing through a very large cross-sectional area, right? So its velocity becomes the velocity of the gas over here becomes low, right? And that decrease in velocity helps the particulate matter in the gas settle down. Because particulate matter is supposed to be heavier than gas molecules, so what happens is the heavier PM settles down and the gaseous molecules just pass through the settling chamber and are collected on the other end. So on the other end of the settling chamber, we get relatively clean gas. At least the very coarse particulate matter, which is much heavier, that is removed due to gravity in the settling chamber, although the lighter particulate matter still remains in the gas, but we achieve relatively cleaner gas, right? So settling chamber is one of the very basic technology for the removal of particulate matter from stationary sources, right? And it can only handle very large particles, because the principle on which it is working is the gravity, right? So gravity is significant for the very large particles. Of course, if the particles are fine, and the particles are normally fine, for those, gravitational settling chamber is not a very effective technique, right? So this is how the gravitational settling chambers look like in the industry. Normally, sometimes insulated, because if we are processing hot gases, we don't want those hot gases losing heat in the surroundings, so we insulate our equipment, right? Next option that we have to remove particulate matter for stationary sources is cyclone separators, right? It's a conical shaped equipment in which we introduce the dirty gas tangentially, right? Dirty gas means, let me repeat it again for everybody. Dirty gas means it's a mixture of gases which contains particulate matter, and our objective right now is to remove particulate matter from the rest of the gases, right? So we introduce that dirty gas tangentially in this conical shaped equipment. So this tangential introduction facilitates the dirty gas to move on a circular path, right? And the gas spirals downward, right? And we know when a mass moves on a circular path, that experiences centrifugal force, right? It's a basic physics. So all gas molecules and the particulate matter experiences that centrifugal force, but because, and by the way, this centrifugal force is dependent on the mass of the particle, right? And we know that mass of the solid particles is much higher than the mass of gas molecules. So that is why PM experiences more centrifugal force than the gas, and ultimately PM is collected on the wall of this cone or of this cyclone, right? And in fluid dynamics, we study that the velocity of the fluid on the wall is low, is zero, right? Boundary layer. That's what we call boundary layer. So when the particulate matter reaches the wall, over there the velocity of the fluid is low and low turbulence, and ultimately the particle falls down due to gravity near the wall, and the PM is collected at the bottom, while the comparatively cleaner gas moves upward and is collected at the top, right? So that is another option that we have to remove particulate matter out of dirty gas. This is what we call cyclone separators. This is how cyclone separators look like in the real life. Of course, that's another view. Next option is of baghouse filters or simple fabric, right? Over here you see a number of baghouse filters connected with each other in series and in parallel, right? You see one series of baghouse filters, another series of baghouse filters, and these two series are working in parallel to each other. If we look closely at this baghouse filter, this is how it looks like. Over there in the previous figure, over here, it was vertical, whereas in this picture, it is placed horizontally. So we have got options. Either we introduce the dirty gas from inside this baghouse filter. So if we introduce the dirty gas from inside this baghouse filter, it means the particulate matter would be collected on the inner surface of the baghouse filter, and cleaner gas would exit the filter from all of this surface, right? The other option is that we introduce the dirty gas from the outer surface, and we obtain the cleaner gas from inside the baghouse filter. So this is simply filtration of PM particulate matter from the dirty gas, right? We are using filter in this shape because that gives us a lot of surface area, and we know higher the surface area of the filter, the longer we can use that filter before we need to clean it up, right? So this this is how they look like, the baghouse filters look like in the industry. A very versatile option that we have for particulate matter removal from dirty gas is electrostatic precipitators, right? If you look at this equipment, we have got number of plates arranged in parallel, right? And these plates, alternative plates, are connected with the alternative electrodes, right? So what exactly it means is that one of this plate is, let's say, positively charged, the next one is negatively charged, and then the next one is positively charged, and that's alternatively alternative plates are charged alternatively connected with the electrodes, right? So when we pass dirty gas from these channels, which are formed by the displacement of these plates, the particulate matter gets charged due to charge on these plates, right? And then the oppositely charged particle is collected due to electrostatic attraction. As we know, the oppositely charged charges attract each other, right? So if the PM is charged positively, the negative plate would attract it, and that particulate matter would be collected on that plate. So this is versatile because this equipment can handle the particulate matter of different sizes, right? Whereas in the previous examples, that previous options that we have discussed, every equipment has got its own limitations because those equipments were exploiting the mass of the particle, right? And that's why they all have a limit, the lower limit of mass of the particulate matter that they can remove, but they can't remove particulate matter below a certain size. Whereas electrostatic precipitator, because it is not dependent on the mass of the particle, so um, mm, it can handle all sizes of particulate matter, right? So it is considered an extremely versatile, but at the same time, of course, it is costly, and it is cost effective under certain conditions, right? So choosing electrostatic precipitator, choosing any equipment, of course, is always a question of cost effectiveness, right? And this being most expensive, or it's at the same time most versatile, requires, of course, the assessment of cost effectiveness, right? So this is how electrostatic precipitators look like in the industry. Then so far the options that we have discussed for PM removal were dry options, right? Now we are going to talk about some wet options that we have. Wet options means in these equipments we use water to remove particulate matter, right? For example, you've got simple spray chamber, and in this spray chamber, it's a closed vessel which has got arrangement of water showers, right? Different stages of water showers. So dirty gas enters from the bottom, moves upward. The water is showered from the top, moves downward, and in this movement of dirty gas and water in opposite directions, in the somewhere in between, they get a chance to kind of collide with each other, right? And in that collision, the particulate matter attaches some water with it, and that ultimately increases the weight of particulate matter, and particulate matter falls down along the water, and comparatively cleaner gas is received at the top. So basically we are scrubbing dirty gas, right? We're literally washing dirty gas with water and removing particulate matter by increasing its mass, and that mass is increased when water droplets are attached with the upward moving particulate matter. And once mass increases, of course, the gravity becomes significant, right? And that makes the particulate matter fall down along with water, and then we treat this water and recycle this water again for reuse, and we continuously uh, obtain relatively cleaner gas at the top of this vessel. Another possibility of wet scrubber is cyclone separators, right? And in cyclone separators, as we were doing in simple cyclone tower, we introduce the gas tangentially, right? And that makes the gas move in a spiral path upward. And in the same space, we have got water showers, right? So over here, we attach water droplets with the particulate matter. We make the particulate matter move on a circular path. So ultimately, the centrifugal force, which is dependent on the mass, and now the mass of the particulate matter is much higher as compared to that in the simple dry cyclone, right? So you can imagine that in this wet collector or wet scrubber cyclone spray tower, the the efficiency of the PM removal is supposed to be much higher than that in the simple cyclone tower, right? So that's another example. Similarly, we have got another type of wet scrubber, which is Venturis scrubber. The dirty gas is entering from here, and then over here we have got a very narrow slit, a, a narrow path through which the gas is passing, and at the same time we have got water inlet provision over here. So a mixture of water and gas is passing through this extremely narrow path together, right? The water and the dirty gas is passing through this slit. So it means that there is a higher level of contact, higher degree of contact achieved between dirty gas and water, right? So the chances of PM attaching water droplets are much higher in this case, right? But at the same time, of course, because you're passing this mixture of liquid and gas through a narrow passage, narrow slit, so you really have to push the gas through it, and you require a lot of much higher amount of energy to make that happen. So, but at the same time, you achieve higher degree of contact between the gas and the water, and that leads to higher degree of removal of PM from the gas, right? And then we have got a cyclone again over here at the downstream, which helps us in removing those wet particles from the gas, and cleaner gas is obtained at the top of the vessel. Now, so far we have only talked about removal of particulate matter from stationary sources, and now we are going to talk about gaseous pollutant removal from the stationary sources, right? There are gaseous pollutants, I hope you're familiar, like SO2, like NOx, oxides of NOx, like carbon monoxide, like hydrogen sulfide, and there are number of toxic gases um, which are in most of the cases which are product of combustion system. Combustion system means furnaces, boilers, which are extensively used in the industry. And in some cases, the gases, the pollutant gases can also be a product of the process itself, right? For example, you go to a gas field. Gas field means the place where the process the gas coming from the wells, right? And the gas coming from the wells contains a lot of toxic gases, like for example hydrogen sulfide, extremely toxic gases that can kill human beings even at the concentration of ppbs. So of course when they deliver that gas for domestic purposes, they remove that H2S out of that gas, right? So in on the gas fields, H2S is an extremely common gaseous pollutant, which is not a product of combustion, but rather that is product of the process itself. So we are going to talk about gaseous pollutant removal and the options that we have to remove gaseous pollutants for stationary sources. The first option or technique that we have is that of adsorption, right? Adsorption means we have got dirty gas, and then we make that dirty gas contact with certain solids, and those solids have this ability to attach certain pollutants in that dirty gas, right? Certain pollutants, and normally these solids are supposed to be having larger surface area in the form of cracks and pores in them, right? Normally we use activated carbon extensively for the purpose of adsorption. We also use a lot of natural and synthetic zeolites, which have got higher degree of cracks. No, normally these cracks are not visible with the naked eye, but of course you have to use sophisticated microscopes to measure and quantify and look into the pores and the cracks, right? So what exactly these pores and cracks do is they provide a lot of surface. So a lot of surface means a lot of contact between dirty gas and that solid, and those surfaces, all those surfaces have got this potential to absorb certain pollutant in that dirty gas, right? Normally VOCs are extensively, VOCs means volatile organic compounds, are extensively removed from the dirty gas using this phenomena of adsorption, right? So for example, over here we have got activated carbon, which has got a lot of cracks and pores in it. So when the dirty gas comes in contact with this activated carbon, molecules of VOCs are attached on the surface, and the cleaner gas is obtained downstream, right? So this whole process occurs in a closed chamber, of course, and we can generate or adsorb it later using thermal and chemical processes. The second option that we have for gaseous pollutant removal is that of absorption, right? I would like you to focus on this figure first, right? What we have over here is just like the spray chamber that we used for PM removal earlier. What we have is an inlet at the bottom through which we are introducing dirty gas. Then we have got showering arrangements over here and then we have got outlet for clean gas now. But this whole arrangement is, I mean, it looks similar, but there are certain differences between the wet scrubber for particulate matter and the absorption column for gaseous pollutant removal. And that difference is normally we don't use water, rather we use uh, specifically designed and manufactured solutions, right, through these showers. Now, what exactly those solutions do is that those solutions have got affinity to absorb a particular pollutant selectively, right? For example, we have got, let's say we have got natural gas, which contains a lot of H2S, as we discussed. And of course, we are supposed to be removing H2S from natural gas. So we pass that dirty natural gas through this column, and this solution absorbs most of the H2S out of it, if not all. Of course, we expect industrial processes not to be 100%, rather even 99.9% is good enough, or even more than enough. So this solution absorbs H2S, and we get cleaner gas at the top, and then at the bottom, of course, we have got solution which contains H2S. So we take that solution in another vessel, and we get that H2S out of that solution. We make use of that H2S. We use it as the raw material for sulfur production that we use again in medicine and different industries. And then once the liquid is free of H2S, we reuse it again, we shower it, and we process further gas. So that's how we absorb the pollutant in a solution, and we make the dirty gas free of that particular pollutant. And that's why we call it absorption process, and we call this tower as absorption tower. There can be different forms and shapes of absorption tower. For example, over here we have got a packed column absorption tower, which is filled, which has got beds of packing material, right? Packing materials are loose items of plastics or in some cases metals. So these packing materials provide a lot of surface. Again, the dirty gas enters from the bottom, the liquid or the solvent which is supposed to be absorbing the pollutant, that enters from the top, and this packing material offers a lot of surface area on which the dirty gas comes in contact with the liquid, and during that contact, the solvents absorb the pollutants from the dirty gas, and at the top we get gas which is free of that particular pollutant for which this solvent was designed to absorb, right? And then yet another type of absorption column is the one in which we use plates, right? So there are different stages, and in this on these plates, the gas again moves from bottom to top, the liquid moves from top to bottom. They travel in opposite direction, and while traveling in opposite direction, they make contact with each other, right? And during this contact, again, the pollutant is absorbed. In literal terms, the pollutant is transferred from gas to the liquid, right? And then that liquid containing that pollutant is obtained at the bottom. At the top, we get cleaner gas. So there can be different types and arrangements and formats of absorption occurring in the industry, right? The last option that we have for gaseous pollutants is incineration. Now, what exactly we mean by incineration? Means combustion, right? Literally, we burn the pollutants. And we burn the pollutants because combustion is a chemical, it's an oxidation reaction. I hope we all can understand that combustion is a reaction in which the fuel reacts with oxygen and gets oxidized, right? There are pollutants which are less toxic in their oxidized form. For example, if we burn H2S, we get SO2 and water, sulfur dioxide and water. Sulfur dioxide is still a pollutant, but not as toxic as H2S, right? We can tolerate certain degree of SO2 concentration in the air. We can't tolerate the same degree of H2S in the air, right? So what we do is, before venting the H2S into the atmosphere, we pass it through incinerators which burn that H2S and transform that into SO2. So what we do is we have got dirty gas that enters from let's say here, and then we have got a flame over here, and that dirty gas passes through the flame, which means that is burnt. H2S is burnt, and ultimately that is transformed into SO2 and water, and then that passes through a catalyst which further enhances that reaction, and ultimately at the top we have got purified gas, or a gas which is free of H2S, at least, though it still contains SO2, right? So that's how we deal with certain pollutants, particularly pollutants, the gases which are combustible. We use incineration, right? Or the gases which don't have any further value, so we burn them before releasing into the atmosphere. Um, if we look at the end of pipe treatments for mobile sources, one very commonly used technique is catalytic converter, right? You must have read it written on some cars that this has got catalytic converter, right? Now we have combustion in the vehicle engine. We burn fuel, and that combustion gives us certain pollutants, which mainly if we are using gasoline in the engine, that mainly gives you oxides of NOx, CO, and hydrocarbons, with of course some other gases, but these are the three major pollutants released from the gasoline engine. Or if it is diesel engine, normally we don't get that much CO, but we get much higher amounts of nitrogen oxides and hydrocarbons from the diesel engine. So again, we have option before letting the gas exit out of the tailpipe. We pass the gases coming from the engine through a reactor which is called catalytic converter, right? Catalytic converter is a small, as it's a small kind of equipment. It's a reactor as it's shown on the in the picture, which has got certain chemical, right? Over here you see a honeycomb structure, right? And that has got a lot of pores. So the gases pass through these pores, and on this honeycomb structure, this is basically made of ceramic, which we call substrate. And on that ceramic we have got coating of wash coat, and in that wash coat we have got active catalyst suspended in the wash coat. So basically it's the active catalyst which helps these gases, these toxic gases coming from the engine, converted into less toxic chemicals, right? We're going to look at those reactions later, but we are over here we are just looking at the arrangements that we use in catalytic converter. So essentially it's a reactor through which the toxic gases coming from the engine pass, and this reactor converts those toxic gases into non-toxic or less toxic uh, gases, right? So that's the option that we have for vehicles, and that is since early 70s the industry is using catalytic converter. It has got its own limitations, it has got its own strengths, but for common cars which are fueled by gasoline, it's practically that's the technology that we have right now, right? Of course we can decrease the emissions by changing fuels, as we discussed earlier, or we can also decrease the emissions by changing by upgrading the technology. All those options are there, but at the end of the pipe, whatever emissions we are getting, catalytic converter is one good option that we have, and what we are practicing extensively in the industry. So if we look at the reactions that that occur in catalytic converters. There are types of catalytic converter. There is a two-way catalytic converter, right? And that only oxidizes the CO2 and hydrocarbons, right? When we oxidize CO, that forms CO2, which is of course less toxic, right, as compared to CO, which is highly toxic. Similarly, when we oxidize the hydrocarbons, we get CO2 and water, carbon dioxide and water. Then there is another type of catalytic converter. And by the way, mm, okay, then we have got three-way catalytic converter, which is which performs the task of converting CO and hydrocarbons into their less toxic version, but at the same time that also deals with the oxides of nitrogen, and that transforms that oxide of nitrogen into reduced form of nitrogen, which is nitrogen itself. So and there is a third type of catalytic converter, which is called selective catalytic converter. Normally we use it with diesel engines, and that converter is designed to handle one particular gas at a time, right? Normally we deal, for example, NOx, and we reduce NOx into nitrogen and less toxic gases using selective uh, catalytic converter. With this, I finished my presentation. I had to rush through the slides because we lost 10 minutes at the beginning. So I hope we do have a question answer session separately. I'm expecting lots of questions because I know I have rushed through the slides, but I really wanted to cover all those slides in this presentation just to give you an idea.
Thank you, Dr. Zeeshan.
Over
It
to
was
Dr.
a
Fahim.
yeah. Thank you very much. It was very interesting. There is a Ali. There is a slide change just to make audience. We can have a quick couple of questions after each talk, so that will keep the audience active and more participatory mode rather than we click the question at the end of each session. So the session is open for question and answer session. Please raise your hand if you have any questions and we can ask. So the first question is from Mr. Iftikhar Saib. Please go ahead.
Yeah, actually,
Yes.
I have a very simple question from Dr. Zeeshan. First of all, thanks for such an elaborate and very understandable presentation. I was wondering which of the two techniques among the Venturis scrubber and the electrostatic plating is going to be the best one if you want to choose based on the efficiency. Which one would be the best one, the Venturi or the electrostatic plating?
Okay, I got your question, and that is an excellent question. The choice of a particular technology for a particular application, that is something I really skipped because of the time limitations. So Venturis scrubber and electrostatic precipitator. Generally, electrostatic precipitator is supposed to be having higher cost, right? Higher cost of operation as well as capital cost. And when we say higher cost of operations, of course, we're talking about operation and maintenance cost. If, as long as Venturis scrubber delivers you the PM removal, you would go for Venturis scrubber. But the strength of electrostatic precipitator is that it can handle a variety of, it can handle a vast range of particulate matter size, right? There are processes which generate particle of a particular size range, a small size range. In that case, of course, you can choose any other equipment than ESP. But if your process is generating particulate matter of wide range, normally you would go for electrostatic precipitator, right? Secondly, if you're treating very hot gases, in that case, of course, you have got limitation because Venturis scrubber uses water to remove particulate matter, and you don't want that lot of steam generation in your Venturis scrubber. So in case the gases are very hot, probably you would be going for drier options, right? And drier options means uh, if again if you have high requirement of PM removal, which means you want the clean gas to be very clean, of course in that case you will be going for electrostatic precipitator. Sometimes your gases are explosive for them, right? And in that case, of course, ESP has got its own limits because of all those electrostatic kind of mechanism involved in that. So, and another thing one that you have to understand is electrostatic precipitator can accommodate a wide range of flow through it. So if the flow rate is varying a lot, if the flow rate of the dirty gases is fluctuating at higher degree, in that case, all those equipments which work on the kind of principle of gravity or centrifugal force, those have got limits. Those are designed for a particular flow, and if there is fluctuation in the flow, they have got their own limits. On the other hand, electrostatic precipitator does not have that limit. Rather, it can handle uh, a wide range of flow rate of dirty gas, right? So the choice of which particular technology over other one is a bit more complex. I hope you understand after all these factors. But and if you still have confusion, we can discuss it more.
It's okay. It's okay. Thank you very much.
Okay.
Thanks for the elaboration. I got it.
I see hands. Dr. Fahim, are you coordinating?
Hello, sir. Assalamu alaikum.
Walaikum salam. Who's this?
Sir, I am Rabia Said and I'm Master's of and student of Environmental Science.
Okay.
Actually, sir, this presentation was amazing, but the thing is, I live in Quetta. So, Quetta is not an industrial city, and we have air pollution basically due to the vehicles. And the vehicles' condition are drastically horrible here. So what happens in summer, particularly that we have that black cloud of gases and in troposphere, and we don't have such policy. And what kind of in that scenario, what kind of procedures that we can establish over here? Because Quetta landscape is like that; it is surrounded by mountains, so that dirty gases don't spread out to the other regions, and they are trapped within that area. So in that scenario, what kind of a procedures do you think that we can implement to clean out those dirty gases?
Okay, that's an excellent question, Rabia. See, the valley-like topography is always challenging, whether that is Kathmandu or Quetta. If a space is closed like a valley, then the ventilation is restricted, as you have mentioned, right? So it is always challenging. You have to restrict the source somehow, right? So you're saying that vehicles are the major source of air pollutants. Maybe then you have to look into the transportation modes. Maybe you have to introduce mass rapid kind of these metro type buses, or if we could afford, we could have gone for electric trains, which obviously don't have pollutants released from them. The other thing that you can do is you can have policy of discarding older vehicles, right? Because what we have, for example, one of my students studied in Islamabad that there are only 5% older Mehrans and the vehicles which are cars which are older than 20 years, right? And they release more than 30% of the pollutants of the vehicular fuel. So their contribution in the emissions is much higher than their fraction in the number. So you can consider having a policy of discarding older vehicles. And I mean, in urban areas, they do have. In developed world, of course, they have this policy of using lesser vehicles. Right? They achieve it by introducing uh, collective modes of transportation. Sometimes they go with this policy of using even numbers and odd number vehicles on alternative days. That helps in reducing the source. And you can propose that we implement this policy particularly in those seasons when the problem is really kind of exacerbated by the meteorological conditions. I'm sure Dr. Fahim yesterday discussed that in certain weather conditions, the air pollution becomes bigger issue than the other parts of the year, right? Other days of the year. So they can adopt these measures at least in those segments of the year when the pollution is really a bigger issue than the normal situation. I hope that answers your question.
Yes, sir. Thank you so much.
जी डॉक्टर आसिफ आप कुछ सवाल है you have raised your hand.
Yes, thank you very much, Dr. Zeeshan, for such a nice presentation. It was very elaborate. Just have a quick question. It's related to the electrostatic precipitators and the particulate matter. For example, if we talk about soot particles, they are usually negatively charged, and they are attracted to the positive side of the electrostatic precipitators. Can you please shed some more light on whether there would be possibility of other types of particulate matter being attracted to the other side of the electrostatic precipitator? Thank you.
Okay, of course, the particulate matter, which is, if it is charged positively, then it's going to get attracted to the negatively charged particles, and vice versa as well. So it works in two ways. Right? I mean, the oppositely charged particles are going to be attracted toward the oppositely charged plates. So can you please repeat the question if that doesn't answer that?
No, that's perfectly right. But one actually determines whether these particulate matter will be either positively charged or negatively charged. I know it's their chemical background, but in addition to that, are there any other environmental factors that can play a role in this? Thank you.
That's true. See, the moisture in the gas, that can play a role, because when we say dirty gas, if the gas is coming from combustion system, in that case, that is supposed to be having a lot of moisture in it, right? And that is going to alter the surface characteristics of the particle. And charge is a surface property. I mean, the nature of the surface of the particulate matter determines how much charge it's going to accumulate passing through a particular electric field. So when there is a change in humidity in the gas, that is going to kind of alter the surface nature of the surface of the particulate matter, and that's going to affect, to some degree, that is going to affect the kind of efficiency of the electrostatic precipitator. Sometimes we do get changes in the, see, suppose you change the fuel, right? Fuel quality always changes. Even if we don't change the fuel, the quality of the same fuel changes sometimes, and then that also changes the composition of the gas itself, right? For example, on a particular month, you get a fuel which contains lesser level of sulfur or lesser level of lead as compared to, and the next month you get fuel of a different quality. So that ultimately changes the composition of the flue gas, right? So a different flue gas passing through the same electrostatic precipitator, that's going to affect.
Apologies, guys. We have to move. I'm sorry for interruption. We have to move for the next speaker because we are running late of the schedule. Please. Sorry, don't mind. We can continue this discussion after all these presentations.
Sure.
बिल्कुल. Thank you, Dr. Zeeshan, for the insightful session. I'm a very and thank you, Dr. Asif, for asking a very relevant and energetic questions. Thank you for being relevant and taking part in the engagement part. Dr. Fahim, is it possible that we take a 2 minutes, just a 2 minutes break, just a chai sip break before we start the next session, and we'll also pause this recording of this session.
So if